In this video, we will be talking about centripetal force. So you've talked about, wait, you know what? Let's write it down. Centripetal force. So you've talked about centripetal acceleration. I need better handwriting there. You talked about centripetal acceleration. So a centripetal is equal to velocity squared times radius. So your tangential velocity while going around in a circular motion divided by the radius, or the distance from the center of your circular motion, is equal to centripetal acceleration. And this centripetal acceleration accelerates you so that you don't fly off. So if you're going in a circle, your centripetal acceleration has to pull you in. And if it doesn't pull you in hard enough, well, you just go flying off. Maybe the path would more look like this. But we're going to be talking about centripetal force. And I just wanted to recap the idea of centripetal acceleration real quick. So here's the thing about centripetal force. Take a guess, what's the centripetal force formula? Well, if you've guessed, all you need to do is multiply acceleration by mass, and you get centripetal force. So this side becomes mass times centripetal acceleration is centripetal force, and the other side of this equation becomes velocity squared times mass over radius. So using centripetal force, you'll be able to solve for certain problems, and they're pretty helpful when it comes to solving for banked curves problems. And maybe if you want to calculate the centripetal force required to accelerate a proton around a particle accelerator, that might help, which is actually one of the questions that I'm going to be covering today. That's enough yapping. Let's get into some problems using this centripetal force formula. In this problem, you have two parts, and I don't know if I'm legally supposed to do this, but I have to I search it up. I think I have to shout out BlueStacks. So if I use any problems from BlueStacks, it's an online textbook. I have to I don't know, give credit to them or something. But these problems, these online problems, there's a lot of they have a lot of textbooks. They're all free, and they also have practice problems in the textbooks. But I think I'm going to start to get the practice problems in them because it's better than me making my own. But the first part of this problem is a 20-kilogram child is riding a playground merry-go-round. So again, there's some mention of rotation. Rotating at 40 revolutions per minute. What is the centripetal force? What centripetal force exerted if he is 1.2 meters away from the center? So let's mark our information. We need the radius for our centripetal force formula. So we have 1.25 meters as the radius. We also need velocity and mass. We have the mass, 22 kilos, but we don't have the velocity. We have the 40 revolutions per minute. This is kind of a measurement of speed here. And how do you solve for this? Well, in order to change this tangential velocity, you need to do some unit conversion. So in order to do some unit conversion, I need to calculate the circumference of my merry-go-round first, or the circumference of the child's path. And the circumference of this child's path is just 2 pi times the radius. So the circumference in total is equal to 2.5 pi meters. This is the circumference. So the circumference is 2.5 meters, 2.5 pi meters. That's the distance for one revolution. So we can actually do some unit conversion, and we can turn this 40 revolutions per minute into meters per minute by writing down 1 revolution down here and 2.5 pi meters up here. And the revolutions unit cancels out, so you just get meters over minutes in the resulting unit conversion. And we can also convert minutes to seconds because we want meters per second in the end of our answer. So we can write down 1 minute up here and 60 seconds down here. And in the end, these minutes cancel out, and you get left with meters per second as your units. So all you need to do is multiply 40 by 2.5 pi, divided by 60 seconds into your calculator, and then you will get a tangential velocity in this case. And once you do that, you should get a speed of 2.4 meters per second as your velocity. So once we have our velocity, we could just multiply everything together. We can multiply velocity, 5.24 squared, times meters, times mass, times mass, 22 kilos, over 1.25 as the radius. And your centripetal force should be equal to 483.25, approximately, newtons. So this is the force required to keep the child within the spin of the merry-go-round. Now, how about part B? What centripetal force is exerted if the merry-go-round rotates 3 revolutions per minute and he is 8 meters from the center? So I'm just going to erase this part since we don't need it anymore. Put that against writer information. So our new radius is 8 meters. Our kid's mass stays the same, 22 kilograms. But we still need to find the velocity. So again, we'll do some unit conversion. So revolutions over minutes. Let's convert revolutions with the circumference on top. So the circumference is equal to 2 pi times radius. So if we just multiply 2 pi times the radius, you'll get 16 pi. And then once you get 16 pi, you can write 16 pi meters at the top here. Since radius was in the unit of meters, your circumference will be in the unit of meters as well. So unit conversion, basically just treat the units as variables. You can cancel them out like so, using some algebra. And then again, we want to turn minutes into seconds, so we can get meters per second. So 1 minute up top and 60 seconds down below. And these minutes cancel out, so as a result, we get a tangential velocity of 2.513 meters per second. Now that we have the velocity again, we can just calculate our centripetal force directly using our formula. So 2.513 squared times your mass of your kid, 22, over the radius divided by 8. And in all, that equals 17.37 newtons, which is significantly less than before. The previous answer was somewhere in the range of 483 newtons. And the reason why is because, well, if you're making a super tight turn in your car, so let's say you're driving your car and you're making a super tight turn, you'll feel the pulling force more. Technically, what you're experiencing is called the centrifugal force, but that's a non-existent force technically. But the tighter your turn, the more you have to accelerate, so the more you feel the turn. But the further you're away, the wider your turn, right? In this case, 8 meters is a wider turn than 1.25 meters. You'll experience that force less, and the centripetal force is significantly less if you get further away from the center. So the center, if it's 8 meters away, it's 17.37 newtons, which is significantly less than 483. But also your speed matters as well. If you make a super slow turn around a curve with your car, you won't really feel much of that acceleration. But on to the next problem. So for this problem, as I said, you're going to have a particle accelerator problem. And the reason why I picked this is because I like particle physics. And currently I'm reading a book called The God Particle. So I don't know, it doesn't even talk about the Higgs boson in that book. Okay, you know what? You guys definitely don't care. I'll just do the problem. Alright, so the CERN particle accelerator is circular with a circumference of 26.7 kilometers. So 26.7 kilometers is the circumference. But 26.7, okay, you know what? I'll write this better. 26.7 kilometers is also equal to 26,700 meters. So it's 26,700 meters. What is the acceleration of the protons that move around the accelerator at 5% of the speed of light? Okay, this is supposed to be 10 to the power of negative 27, but the copy and paste didn't work out very well. Just think of this as 10 to the power of negative 27. So now that you try to solve for this problem, what is the acceleration of the protons that move around the accelerator at 5% of the speed of light? Well, we were given the speed of light here. It's approximately 3 times 10 to the power of 8 meters per second. If you multiply this by 0.05, you should get a velocity of 1.5 times 10 to the power of 7 meters per second. And this will be our velocity in this case. And if you, okay, let's remove this velocity so we can move this down. And if you multiply velocity squared times the mass over the radius, well, you will get your centripetal force. So we have our velocity already. That was easy to calculate. It's just 5% of this guy right here. And now we have the mass. It's already given. The mass of a proton is 1.67 times 10 to the negative 27 kilos, which is the correct unit. So always make sure it's the correct unit. The reason why I turned the kilometers to meters immediately was because you don't want to do the calculations with the wrong units. But what's important here is actually the radius. We have the circumference, but we don't have the radius. But remember, the circumference is just equal to 2 pi times r. So if we divide the circumference by 2 pi, we should get r. So if you divided circumference by 2 pi, you should have gotten a circumference of about 4,249.44 meters. Oh, radius. Sorry, not circumference. Radius. Now we have all the tools we need in order to solve for our centripetal force. So let's do 1.5 times 10 to the 7 squared times a mass of 1.67 times 10 to the negative 27 kilos over the radius, which is 4,249.44 meters. And type this all into your calculator, and you get 8.83 times 10 to the negative 17 newtons. So it's actually, it doesn't require that much force to move a proton. It doesn't require that much force to accelerate a proton in a circle, since it's so small. For this problem, we have to solve for the maximum speed at which a car can traverse the curve without slipping. So this one, you have to derive an equation. And it's a little tricky because the friction being your centripetal force isn't as obvious as you think. So if a car was going around an unbanked curve, which means the curve isn't elevated or angled upward, the curve is just complete, it's a flat road. When your car is going around this curve, your static friction, so the friction of your wheel tires, kind of prevents you from flying outward. Let's say you were driving in a curve and immediately out of nowhere the ground becomes frictionless. Well, you would fly in this direction. You kind of fly in an outward direction like so. So what's actually happening is when you're turning, your friction of the tires onto the road is actually pulling you into the center. It's actually not necessarily pulling you to the center. It's preventing you from flying outwards. So the friction when you're driving is your centripetal force. But here's the thing. Static friction has a limit to how much force it can create. And that limit is dictated by the normal force times the static friction coefficient. And that's the maximum amount of friction, static friction, that you can produce. But why is that important? Well, the maximum amount of static friction you can produce since static friction is centripetal force in this case, that means the maximum centripetal force you can produce is your static friction force. So if we multiply, if we create an equation here, mass times gravity is equal to your weight. In an unbanked curve, your normal, or a flat plane, your normal force is equal to your weight. So mass times gravity is equal to weight. And you multiply it by your friction coefficient to get this entire thing is equal to static friction or centripetal force. Now, all you have to do is set this equation equal to your centripetal force equation. Centripetal force is equal to centripetal force. Who knew? This is also centripetal force. Did I use a different color? That looks like a darker red. This is also centripetal force here. This is the formula for centripetal force, and your friction produces your centripetal force. So you can set those two equations equal to each other. What actually happens is, well, when you were reading this problem, you were probably thinking the mass of the car wasn't given. How do we solve for this? Well, the mass of the car can actually be canceled out here on both sides of the equation. So what you get left off with is mg is equal to velocity squared over the radius. So if we were to just isolate your velocity, you would get, oops, not mg. You would get gravity times the static friction coefficient is equal to velocity squared over radius. And if you were to isolate velocity, you would get the square root of radius times gravity times static friction coefficient is equal to velocity. In this case, max velocity. So we actually have all those values. We have the radius given here, 65 meters. Gravity is a given, 9.8. And your static friction coefficient is 0.7. So what it actually turns out is that the mass of the car doesn't matter. You can actually cancel out those values. So your velocity max would be 65 times 9.8 times 0.7. And if you multiply all this together, you get, and the square root of that, multiply all these together and take the square root of that, you get 21.12 meters per second as your maximum velocity. So, as always, if you have any questions, put it down in the comment section. I hope this video helped.